Welcome back to a continuation of our series on off-highway vehicle design. Today we're talking about brakes. So why do we have brakes? You might think that's an obvious answer, but it's not always. The brakes are there to absorb the energy of the moving vehicle and to dissipate that energy later. But it's often more than just the vehicle itself. I've seen concrete mixers where the vehicle brakes were expected to break the bowl of the concrete agitator, and that was a considerably larger amount of energy that had to be absorbed. So the brakes are there to absorb the energy of the moving vehicle and the relative associated moving parts. There's of course a variety of brake types that you might see off highway, and we're going to look at a few of them now. So here's the good old drum brake. The drum here is semi-transparent, but we'll see a pair of shoes, a wheel cylinder to expand them out onto the drum, some springs and adjusters. Older cars, and I've got to say some modern ones use drum brakes. They're really good until they're not. Basically don't ever get them too hot because they don't dissipate the energy very well at all. Mostly these days, at least on cars, you'll see disc brakes. Rotating rotor, and then a brake caliper with at least a couple of pads and some hydraulic pistons. This is probably the optimum for lighter vehicles because it has all of this surface area to dissipate the heat. This is in fact a ventilated disc brake rotor to make the heat dissipation even better, and this is probably the brake we would all aspire to use if we could. I'll get to why we might not in a little later. In more difficult circumstances, we have a multi-disc brake. Now this is a Clark Posi-Stop. It's a part cross section of it. This is the center line of the axle here. This is the planetary hub. And here there's a stack of brake discs. Now they're not the sort of brake disc you're used to on a dry disc brake. These are thin discs that essentially have material sintered onto them, and each alternate disc is either connected via a spline to the rotating hub or via a spline to the fixed hub, and hence the relative movement of the discs. When these discs are squeezed together, you get friction between a rotating element and a stationary element. This is a mining type brake for a couple of reasons. This particular version is what's called SAR, Spring Applied Hydraulic Release. So here's the spring here pushing on a plate which then squeezes all the discs together. To take the brake off, you apply hydraulic pressure and pull this plate back. Now there's several very important reasons for using a multi-disc brake. Firstly, they're oil immersed. So theoretically, brake discs never touch each other. Perhaps when the vehicle is completely stopped and everything is squeezed together and stationary, they will. But in service, they theoretically at least work by shearing the oil between the two plates. So that of course puts the heat, the energy, into the oil, which then has to be maybe cooled, or the heat otherwise dissipated through the structure and out to atmosphere. In mining, these are great because they're totally enclosed. You can drive through mud, slush, whatever you want, and it won't get into the brake. The downside is they tend to run hot, particularly at any sort of increased speed. 30 kilometers an hour or above is about the maximum for a wet disc brake, an oil immersed wet disc brake, which is what these things are called. Faster than that, if you insist on using this sort of brake, you better be prepared for a lot of cooling, a lot of additional cooling, and maybe a reduced life. And just to be complete, this is what I call a block brake. It's also apparently called a class brake. It's a typical railway arrangement. There's a brake block here that's pushed against the outside of the wheel to brake a rail vehicle. And this is used on the vast majority of rail vehicles operating. We probably won't talk much more about this today because it's a fairly simple pneumatic arrangement. So we would all like to use dry disc brakes, the conventional brake discs. The problem is that if you're operating in mud and slush, those discs and the pads don't last very long. They're very susceptible to dirt ingress and the creation of excessive wear. Operating four-wheel drives, commercially available four-wheel drives in quarries and open cut mines, they can get very short lives on their braking components just because of all the muck that's inside, gets inside the caliper and onto the disc and basically grinds everything away. Doesn't happen with fully enclosed wet disc brakes. The other sort of braking is typically called regenerative, and that's where you put the energy back through your drivetrain. In a diesel electric locomotive, that can go back, be used electrically to drive things, or put across a resistor bank and the energy just dissipated to the atmosphere. Regenerative is a little bit of a tricky term. If you drive a Tesla, your braking system probably is primarily regenerative. You're regenerating and putting the energy in a battery. But if you drive a manual internal combustion car, when you change down, going down a hill, you're essentially using dynamic braking or regenerative, in that you're putting the energy back into the power source. In that case, running the internal combustion engine as a compressor. In general, dry disc brakes are the best performers because they can dissipate the energy they absorb the quickest. Drum brakes are really good until everything gets hot, and then they're really lousy at dissipating energy. And wet disc brakes, right thing to do for a lousy, dirty, muddy environment. And in coal mining, they're used exclusively underground because they can't get a hot surface. They are oil immersed inside a housing. So if we talk a little bit more about multi-disc brakes, they are used almost exclusively in underground coal mines because they're enclosed and oil immersed and so forth. The SAR brakes, the spring applied hydraulic release ones, are also ubiquitous because that gives you a level of safety. If the hydraulic system fails, the brakes come on. And hopefully they've got a wear indicator too, so that you don't have to pull the thing apart to find out if it's worn or not. And yes, they do wear. As I said, theoretically the brake discs never touch each other, but in reality they still wear. So the controls for all of this, well, it's sort of dependent upon what brake system you use. If it's a railway block brake, it's going to be pneumatic. If it's a multi-disc brake, Yes, it can be electric, it can be pneumatic, but it's primarily going to be hydraulic. And if it's a dry disc brake, almost exclusively it will be hydraulically operated through a master cylinder. There are occasions when you use a dry disc as a park brake, and that's mechanical, but you know, that's fairly rare and on light vehicles only. If it is through the hydraulic system, and by that I mean you've got a vehicle that might have hydrostatic drive and a lot of hydraulics on board, as opposed to a master cylinder, slave cylinder hydraulic arrangement, then the normal practice would be to give priority flow to the brakes. Hydraulically driven vehicles normally have priority given to brakes and steering before any ancillary functions. And that's purely for safety reasons. And that gets us onto the subject of safety. Obviously brakes are very important to safety, and for slow speed vehicles it's almost obligatory to have fail-safe brakes. Now what that means is whatever happens in the system, hose blows, lever falls off, who cares what, the brake's default position will be on. Certainly the spring applied brakes, that's the condition. You blow a hydraulic hose, the brakes come on. Now for higher speed vehicles, that may not be a safe situation. If you imagine a sports car hammering hard around a corner and the brakes come on, that's probably going to be a dangerous situation. So you may need to think carefully about what constitutes a safe condition, a fail-safe condition for your design of vehicle. For brakes, of course, it's normal to have a split system, not just one system fits all wheels. You at least have two systems, maybe the front, maybe the back, maybe there's diagonal systems to try and ensure some stability, but always try and duplicate your brake systems so that they are split. For us here in Australia, particularly in this state, we have to get involved in functional safety when we're designing for mining vehicles. Now, functional safety sounds a fairly benign term. It is an extremely complex subject that goes into the likelihood of failure, the risks associated with it, the reliability of individual components, the system architecture, and eventually it comes up with a number. That can be a SIL rating or a PL or a CAT number, so that you are able to designate the available safety and reliability of that system. It's a big pain in the butt, but it does head the design of the brakes, and particularly the braking systems, down a much safer path. And I'm not going to get further into functional safety. It'll do your head in, make your brain spin around in circles. Complex, give it to a consultant and let them do it. We're also legally required to do things to a minimum of what's called ALARP. Now that indicates the risk is as low as reasonably practical. ALARP. And essentially that's defined as what a reasonable person would accept as the level of risk associated with the brakes. Now this is not a subject for the faint-hearted. If you drive a standard car, you expect the brakes to work. You don't want to know about risk. Well, the reality is that risk exists. If you get out of bed in the morning, you accept a risk. If you stay in bed, you accept a different set of risks. So there are risks to using the brakes in your car. There is a risk that it won't work because the master cylinder's failed, or a hose has been damaged. I have a problem in my car at the moment where a rear wheel speed sensor has gone faulty. So I've got to be careful with that. And the drive here is now to go beyond ALARP, making the risk as low as reasonably practical, to what's called SFEP, so far as is reasonably practical. Sounds fairly similar. The idea is you can design to ALARP, and I'd say that's designing to a typical industry standard. In underground coal, the braking systems are fairly standardized. The next step is SFEP, which is to look at what is the next step in the design beyond ALARP that you could make to improve the braking system. And if you don't make that next step, why didn't you? Now, money isn't an acceptable answer to that. It could be that the system's more complex, that there are many more sensors and hence the reliability of a failure increases, the system gets more complex and maintainability becomes an issue. But you have to design a safe braking system as far as practical. It needs to at least be ALARP, as low as the risk, as low as reasonably practical. And you should then look to the next stage to see what you can do to make things even safer. And that's SFEP. Now let's talk a little bit about performance. You're designing a vehicle, you're going to need to look at the worst possible case. And what is the worst possible case? Underground coal mining, we know the maximum grades. We actually specified what we must be designing for, generally 1 in 4. But is it 1 in 4 with a heavy load? Is it 1 in 4 empty going faster? Is it on the flat, at top gear, flat out? Which of those circumstances constitutes the worst possible braking system, i.e. the highest energy that must be absorbed? It would typically be the fastest speed, because kinetic energy is a half mv squared, but it could be, if you're a load carrying vehicle, that your load is so significant that even at slower speeds you have the highest energy requirement. So that will tell you what energy your braking system needs to handle for a single stop. But what happens if there's multiple stops? What happens if it's a winding, steep road, where there's a continual set of hairpins? You're going to be on and off the brakes all the time. So you've got to be careful that you can handle multiple stops, or perhaps the worst case, a long decline where you're on the brakes all the time. Yes, there should be a retarder. Yes, there should be converter lockup and all sorts of other things to try and take the load off the brakes. But you must consider a single start, a single stop, and then repeated stops in a short period. That's actually the thermal capacity you've got to be able to handle. So I mentioned converter lockup. Without converter lockup, you won't be able to run the engine as a compressor. As a compressor, the engine will absorb about 60% of its naturally aspirated horsepower as a compressor, and that can be significant. Lockup's necessary so the converter doesn't just spin and disconnect the engine. You may need to actually consider the energy required to turn over the drivetrain. One of my customers has recently done that. Towed a vehicle, engine running, but engine at idle, a vehicle in gear, pulled it forward and measured the resistance of all of the drivetrain. Now, they didn't have converter lockup, and yes, there was a significant result with the vehicle in gear compared to the vehicle in neutral. Big difference, but it wasn't enough from a braking point of view. So this is another example of the vehicle design being holistic. If you're designing the brakes, But here I am discussing converters. It's important that the whole thing work together. Now, brakes are usually part of the axles, so the decision on brakes is probably going to be made way back at the axle selection. But you still need to be confident that they're suitable for the duty, that they will handle the energy and the torques necessary to do the braking. Make sure that the brakes match the overall vehicle, right down to optimal or optional tyre sizes, because when the tyre sizes change, the braking torque is likely to change as well. So be very sure that you've got the right brakes, be extremely confident. Make sure you've got a safe control system, as low the risk as low as reasonably practical, and then confidently move on to the rest of the design.